couple things we were saying last time. So if W is any set, then J plus of W points to the causal future of W. Well, including W itself. You'll see in a little while that we can make simpler statements if we include W. And the boundary of J plus of W is the boundary of the causal future. So the basic case is that W is a point Q. So the boundary of the future in Minkowski space would be the future light cone and its interior, and the boundary of the future would be simply the future light cone itself. And of course, every point on the future light cone is connected to Q by a null geodesic without a focal point. So I just said that in Minkowski space, the future of a point is the future light cone and its interior. The boundary of the future is the future light cone itself. And a point on the future light cone is connected to Q by a null geodesic. And in Minkowski space, there are no focal points on null geodesic, so that's a null geodesic with no focal points. It's a prompt null geodesic. And in particular, no focal points. That's only sufficient, that's only necessary, not sufficient to make a geodesic prompt, but the no focal point condition will be the important one. Now we could consider a more general set W and the boundary of its future. And everything is the same with one addition. A point in the boundary of the future is connected to W by a null geodesic that, as before, has no focal point, but it's also orthogonal to W. Well, this statement assumes W is a submanifold. Let's say a space-like submanifold. So the picture is a little bit like this. If you have for example, if you have a sphere embedded in Minkowski space, you would take all the outgoing geodesics from points on the sphere, all the outgoing null geodesics, and they would make up part of the boundary of the future of W. By our definition, W itself is part of the boundary of its future because we consider W to be in its causal future, since we allow a trivial causal path that consists of only one point. And since a point to the past of W would not be in its future, W is always in the boundary of the future. So the boundary of the future of W is the union of W with points reached by orthogonal null geodesics with no focal point. Well, orthogonal null geodesics that are prompt. Now, why am I talking so much about the boundary of the future? In a while, hopefully today, we will use properties of the boundary of the future to prove Penrose's theorem. But intuitively, the reason we care about the boundary of the future is that we're studying the implications of causality in general relativity. And the boundary of the future is the limit of what's accessible by causality. So a signal from an initial set W can only propagate into the causal future of W. And the boundary of the future of W is the limit of where a signal can reach by causality. So when we're studying the limits that are imposed by causality, it's natural to run into the boundary of the future of various sets. Now, there's something I kind of explained at the end last time, but I want to repeat it again because it's important. So, first of all, the future of a point is always closed. That's because if we have some points, suppose we have some points that can be reached by causal curves from Q. Well, saying that So saying that the future is closed means that that sequence of points in the causal future has a limit also. So we want to prove that a subsequence of the points P1, P2, and so on in the future of Q converges to a point P in the future of Q. Sorry. So I stated that incorrectly. Let me improve it. If a subsequence, really we don't have to talk about subsequences. We just want to say the following. If P1, P2, and so on are points in the future of Q and converge to P star, then we want to prove that P star is in the future of Q. That's what it means for the future of Q to be closed. It's always closed as a subset of M. So to prove it's closed as a subset of M, we want to know that if a sequence of points in this set converges to a point in M, then that point is actually in J plus of Q. Well, since the points Pi and so on are in the future, they can all be reached from Q by causal curves. And sorry, this is true in a globally hyperbolic spacetime. In a globally hyperbolic spacetime, sequences of causal curves have convergent subsequences. So the sequence of curves gamma will converge to a causal curve gamma star. And gamma star is a causal curve from future going causal curve from Q, so it's contained in the future of Q. And if the gamma I go to Pi and the P's converge to P star, then gamma star will be a curve to P star. Yes?
Does the closeness interfere with the fact that we take W to be a submanifold?
Well, here on this page I didn't even mention W. I just took the initial point Q. Any other questions? Now, the same is true if W is compact. Then we have a similar picture. Here's W, here's its causal future. Here's a sequence of points that are in the causal future of W and they converge to some point P star. These points can each, they're all in the future of W, so they can each be reached from W by future going causal curves, starting, let's say, at points Q1, Q2, and so on. Since W is compact, the sequence Q1, Q2, and so on has a convergent subsequence. So it converges to some point Q star. Well, it has, after throwing away some of the P's and Q's, we can assume that the Q's converge to some point Q star. And then the curves from Qi to Pi will converge to a curve, a causal curve, from Q star to P star. I've explained this intuitively. If you try to think it through very carefully, you'll see I've left out one or two minor steps in the argument. So I recommend thinking about it carefully on your spare time and asking me if you run into difficulty. But essentially, because spaces of causal curves in a globally hyperbolic space-time are compact, the future of a point, and more generally the future of any compact set, is always closed. I didn't say it was compact, obviously not. The future light cone of a point isn't compact, but it's closed in Minkowski space. So it's also, in the same situation, the boundary of the future of a point, or more generally, the boundary of a future of W, is closed. You see, if P star is in the interior of J positive W, not in the boundary, then a sequence of points that converge to P star also have to be in the interior, at least after the first few. So if a sequence, so if we're given instead that the P's are in the boundary, then P star must also be in the boundary. To go over that one more time, if P star is in the interior, then a sequence consisting of points converging to P star will be in the interior, not in the boundary. So, therefore, if P1 are in the interior, or in the boundary of the future, and converge to P star must be in the boundary. Any questions on that? Now let's look at any null geodesic and ask what part of gamma is prompt. Well, suppose we know that gamma is prompt as a path from Q to P. Then it must be prompt if gamma from Q to P is prompt, then gamma from Q to R must be also. If R is to the past of P. Because if you could do better than gamma and arrive in the past of R, then by continuing you could arrive in the past of P. Once one causal curve is to the past of another, it just tags along like a junior sibling that can't be shaken away and arrives anywhere to the past of the other curve. So, the only possibility is that the prompt part of gamma is an initial segment. Or all of gamma. Or, okay. So in Minkowski space, all of gamma would be prompt. But if promptness is going to fail at some point P, it will never be restored after that. So, okay. If promptness was false at R, it would be also false to the future of R. So whenever promptness fails, it always fails to the future, and therefore promptness may hold up to some given point. So the prompt set is always in initial segments. Now, the prompt part of gamma is the same as gamma intersected with the boundary of the future of Q. So the boundary of the future of Q we proved is closed. That was closed in M. So since the boundary of the future of Q is closed in M, the prompt part of gamma, which is gamma intersect the boundary of the future of W, is closed in gamma. That's just a general fact about sets. This is a closed set in M, so if you intersect it with a subset of M, you get something that's closed in that subset. So that means that tells us that the prompt part is actually a closed interval. So this is either a closed interval, a closed interval, or else it's all of gamma. So what we're discussing is what part of a null geodesic is prompt, and we decided it has to be an initial segment because once you become non-prompt, meaning you could have done better, promptness is never restored farther in the future. But we also know that the prompt part of gamma can be interpreted as gamma intersected. Well, prompt part of gamma among paths from a compact set W. On this blackboard, W was a point, but now let's generalize to an arbitrary compact initial set W. So now we consider a null geodesic that starts at W. It's orthogonal to W, so otherwise it can't be prompt at all. If it is an orthogonal null geodesic, it's possible for part of it to be prompt. The prompt part, by definition pretty much, is its intersection with the boundary of the future of W. Since we've shown that the boundary of the future of W is closed in M, it follows that gamma intersected with the boundary of the future is closed in gamma. But since we also know that the prompt part is an initial interval, we learn that this is either a closed interval or all of gamma. The important thing of this is that the only way for gamma intersected with the boundary of the future of a compact set to be non-compact, is if all of gamma is prompt. Gamma itself is never compact because a future geodesic, whether spacetime becomes singular or not, a geodesic never has an endpoint. Because if there is a point in a geodesic, that point is in a local Minkowski neighborhood. Spacetime by definition is a smooth manifold. And you can always continue beyond any point in gamma. So gamma, a geodesic continued for as long as it can go, is never going to be compact. It's possible for the prompt part of gamma, it's possible for gamma to be entirely prompt. In that case, the prompt part of gamma and is not compact. But if gamma is not compact in its whole existence, then the prompt part of gamma is always compact. It's a closed initial interval. If you think through carefully the things I've said, there's a little bit of redundancy in my explanation, but to me that helps and understand it. So I may not have given an absolutely minimal explanation. Any questions on this? Now there's one more trivial fact, and then we'll explain something about the boundary of the future that's less trivial. So remember that C, recall that a set C is achronal if and only if there's no time-like path from C to itself. Here we mean a non-trivial time-like path. So for example, with time running upwards, I gave an example of a space-like set that's not achronal. That set curls around in space in such a way that the tangent vector is everywhere space-like, but it's not an achronal set because there are time-like curves between different points. So C is achronal, which is a stronger condition than space-like, if there's no time-like path from C to itself. So I claim that the boundary of the future of W is always achronal. That follows from a simple picture. Suppose you have 2 points P and P prime that are both in the boundary of the future. And suppose there's a time-like path from P to P prime. This is a time-like path. Well, P prime was in the boundary of the future of W, so there's a causal path gamma here, and then there's a time-like path L, and you see that L composed with gamma is a non-prompt path. A non-prompt causal path from W to P. So, because a segment of L composed with gamma is time-like, L composed with gamma is not a null geodesic, and therefore it's non-prompt. And since we were able to reach P prime by a non-prompt causal path, it's not in the boundary of the future. More concretely, we arrived at P prime from a time-like path, so that was a path that arrived a little bit to the past of P prime, showing that P prime is not in the boundary of the future. See, if you can reach P prime by a time-like path, then you can reach a whole neighborhood of P prime by causal paths, and therefore P prime is in the interior of the future, not the boundary. So, any questions there? Yes?
Why a chronal is a stronger statement than the spaceflight?
I tried to illustrate that by this example, which I also explained in a previous lecture. In this picture, time runs vertically, space runs horizontally. Then this is if you can understand the picture, this is a space-like curve. The tangent vector is always space-like, but it spirals around in such a way that it goes forwards in time. Then, 2 points in that path. So, it goes around in space, coming back a little bit to the future. Then 2 points can be connected by a time-like path. Any other questions? So this completes the closedness of the boundary of the future was maybe a little bit subtle, but now we're going to get to a fact about the boundary of the future that I think is actually quite surprising. I'm going to illustrate it by going back to Minkowski space. So, the boundary, so if Q is in Minkowski space, the boundary of the future of Q is a cone. Now, in Minkowski space with dimension d, which I'll call R1d minus 1, what is the topology of a cone? You can see that the cone, topologically, is RD minus 1, sorry, a manifold. The cone consists of points that can be described by t and x, where t is the absolute value of x, and any x. So the cone is simply parametrized by a point in space. We can write down an initial value surface a surface at time 0, let's say, that contains the vertex of the cone, the point Q, and we simply map each point in the cone to the same point in space but at time 0. And that gives an isomorphism between the cone and an initial value surface at time 0. So we learned that the cone is a manifold, although not smoothly embedded in Minkowski space. Intrinsically, this cone in its topology is a perfectly good manifold, Rd minus 1. Of course, as a subspace of Minkowski space, it's embedded in a non-smooth fashion with a singularity at the apex of a cone. But intrinsically, it's simply a manifold of codimension 1. That's always the situation for the boundary of the future. And the proof generalizes what we said from Minkowski space. So I pick a point P, which is in the boundary of the future. I'll draw a local picture near P. So there's a prompt null ray from null geodesic from W that passes through P, and okay, that's one fact. So in 2 dimensions, I would just say that points to the future of that geodesic are in the interior of the future. So in 2 dimensions, we could draw a simple picture. So then in 2 dimensions, the future of W is just the future of gamma. Well, let's say in this picture, the left of gamma. In 2 dimensions, we would just say that everything to the left of that prompt causal curve from W to P is in the future, or that's a local picture near gamma. I haven't told you how to draw the picture far away from gamma. And points to the right are not in J plus or W. Well, in 2 dimensions, I would simply say that near P, the boundary of the future is parametrized by gamma itself. Roughly. That's oversimplified because P might be a focal point. Let's try to give an explanation in any dimension. So we pick local Minkowski coordinates. We'll pick a local Minkowski neighborhood of P with coordinates, what did I call them in my notes? Tx centered on P. And then we just look at the curve. So P is, the coordinates being centered on P means that T and X are 0 at P. And then we look at the curve X equals C for small c. So this curve is parametrized by T. So the picture is going to be something like this. Here's P. Here's the future of our set W. Sorry. Then we have our little Minkowski neighborhood. And in that little Minkowski neighborhood, we have the curve X equals C. Now, if T is sufficiently negative, then the point CT is not in J plus of W. P can be barely reached by a causal path from W. So if you're very close to P in space, meaning C is very small, and T is sufficiently negative compared to C, then you're not going to be in the future of W. It's important that this can happen inside the local Minkowski neighborhood, because we wanted T to be much bigger than C, but C and T can be arbitrarily small. Likewise, if T is much bigger than plus the absolute value of C, then CT is in the future of W. So, just looking at this one curve, x equals C, in the past, we're not in the future of W. In the future, far enough in the future, we are in the future of W. So, there's got to be a greatest lower bound of points that are in the future of W. This point is the first point in J plus of W. Well, we know that J plus of W is closed. So the part of this curve which is in J plus of W can't be an open interval. It can only be a closed interval. So it's a closed interval, and there's a first point in that set. See, it's important that a time-like curve which enters the future can never leave the future, because a time-like curve is only going toward the future. So once you're in the future of some set W, when you go farther, you're even farther in the future. So on the curve x equals C, there's a unique point, which is the first point in J plus of W. Let's call that point S. And S is the unique point in the boundary of the future of W intersect the curve x equals C. So each curve x equals C contains a unique point in the boundary of the future. So the boundary of the future can be parametrized by C, and therefore is a manifold.
Are we
Yes?
using here that we are globally hyperbolic in the topology of globally hyperbolic?
Well, we must be, because obviously if you remove the point S, then it wouldn't have existed.
So specifically, the manifold that we're parameterizing by is the initial value surface that we took from the
No, W was any set, I think.
But I mean, what is C parameterizing?
We have any point in the boundary of J plus boundary of the future of W. We want to know that the boundary of the future of W near P is a manifold. Therefore, the whole discussion will focus on the answer to your question is no, global hyperbolicity is not important. The whole discussion is going to focus on what is happening near P.
I see. Thanks.
Sorry. I may be, well, let me try to think it through and we'll decide exactly what we used. Well, everything will happen in a local Minkowski neighborhood near P. And you see, well, let me draw a better picture near P. We think of the near P as a very good approximation is Minkowski space. So the interior of the past light cone is not in the future of P. So the interior of the past of P is not in the future of W. Since if it was, you see, if from W you could reach a point to the past of P by a causal curve, then P would you'd have a non-prompt causal curve arriving at P. So the past light cone from P is not in the future of W. On the other hand, the future light cone is in the future of W. Now, global hyperbolicity isn't relevant here because we're only using the structure near P, which is a local manifold. Now, then we look at the curve x equals c. So it's parameterized by t. If t is sufficiently negative, we're in the past light cone of P, and therefore we're not in the future of W. If P is sufficiently positive, we're in the future light cone, and therefore we are in the future. The first point has to exist because it's all happening in a local Minkowski neighborhood. So we don't have to worry about global hyperbolicity. It's written carefully in my notes and also in Wald's book, but I think what I'm telling you is correct.
So we've proven that the boundary of J plus W is a manifold, but we haven't proven what manifold this is necessarily isomorphic.
No. There's no general answer to that question. I'll give an example showing that. I'll give an example of a globally hyperbolic spacetime where this manifold is not the same as the initial value surface. Any other questions? So we've learned that the boundary of the future of W has the following properties. It's achronal, and it's a manifold. Now, if M is globally hyperbolic, then we proved near the beginning of the course in the first or second lecture. So M has a Cauchy hypersurface S. We proved in the initial picture that any achronal set C is isomorphic to part of S. Just as a reminder, the way we proved that, we had those integral curves in a we used an auxiliary Euclidean metric that was complete. And then we used it to construct some time-like curves, and mapping any point in C to a point in S that's on the same one of those integral curves, we got a map from C to S. So in the first week of the course, we constructed an embedding of C and S using the integral curves in a complete Euclidean metric. So the boundary of the future of W is a special case of an achronal set. So the boundary of the future of W is isomorphic to part of S. It can in general be a proper part, and I will give an example soon. But it's all simply because it's achronal, it's isomorphic to part of S. And it's also a manifold, so it's isomorphic to a manifold that's part of S. So that means that it's either S or an open subset of S. Oh, sorry. Yes, that's right, sorry. The boundary of J plus of W has the same dimension as S. Well, I should have stressed that this argument here that showed that it's parameterized by C doesn't show just that it's a manifold, but that it shows that it's a manifold of codimension 1. So a piece of S which is a manifold of the same dimension is either all of S or else an open subset of S. Now this has a corollary which is important in Penrose's theorem. If S is not compact, then the boundary of the future of W is also not compact. In general, the only way for the boundary of the future of W to be compact is that it's equal to S itself and S is compact. Otherwise, it's an open set in S, and an open set in S, a proper open set, is never compact. Any other questions? Okay. So, I think I'm going to give a couple more examples. We already gave the example of a future light cone in Minkowski space. Suppose in Minkowski space, we look at a closed ball. Let's say t equals 0 and x equal to or less than r. What is the boundary of the future of that set? So here's the ball B. But there also are outgoing null rays from B. A little hard to draw them on a flat blackboard, but I think you imagine them. We have a sphere together with its interior, and then we look at all the light rays going out from there. So we get something that in 2 dimensions would look like this. Here's B, and here are the null rays. Clearly, that's a manifold, although it has some corners. In higher dimensions, it would take more thought how to draw it sensibly, but I think you can probably all visualize that it's a manifold. A variant of that is to consider the sphere. The interior of B, D, let's say. So t equals 0 and absolute x equals r. Well, if we were in 2 dimensions, the sphere would only consist of 2 points. And then we'd have outgoing and ingoing null rays. And it would look like this. In any dimension, if we take this picture and rotate it, we'll build up the boundary of the future of the sphere. So, again, I can't really draw it, but here's our sphere, which I call D. There are outgoing null rays. There also are incoming null rays. The incoming null rays meet at a point in the interior. So there's an apex of a cone here, and there are corners down here. And with a little thought, you'll convince yourself that that's, again, a manifold isomorphic to the initial value surface times 0, although not smoothly embedded in Minkowski space. What are other examples? Well, I'll save a little bit of time by not describing the ellipse, but not discussing the ellipse, but you could think about what happens in the case of an ellipse. So x squared plus y squared plus 2z squared or something. And t equals 0. You could try to visualize what's the boundary of the future of that set. You should again see that it's a manifold that's not smoothly embedded in Minkowski space. I was going to give one more slightly less trivial example just for fun. So in this example, M is going to be S times the set minus 1 less than t less than 1. And I'm not going to tell you what S is. And then the metric is going to be 1 over t squared minus 1 times something. The purpose of the factor 1 over t squared minus 1 is just to explain why the spacetime ends at t equals 1 and minus 1. It doesn't affect the condition of a curve being causal. This is a Weyl factor in front of the overall metric, and causal curves with or without that factor are exactly the same. So I've only included that factor to explain why we limit ourselves to t being less than 1. So here's a schematic picture. We've got a sandwich between t equals 1 and t equals minus 1. And S runs horizontally. But S could do anything I haven't told you about at big distances. We're only going to look at a small part of the picture. Here's t equals 0. Well, I'm going to assume S might be topologically interesting, but it only is topologically interesting a distance bigger than 1 away from the origin, large compared to 1. So if I take a point, well, if I take any point in the sandwich, what's the boundary of its future? Well, we just have the future light cone in a piece of Minkowski space. We have to truncate it at t equals 1, but that doesn't change the fact that it's a manifold. It's an open ball. Now, if we use the integral curves to map it back into S, which we would embed at time 0, we would simply get an open ball in S. And that's indeed an open set in S, but it's not all of S. And S could have an arbitrary topology, which is different from the topology of this piece. So that illustrates the fact that the boundary of the future can indeed be a proper subset of a Cauchy hypersurface. Any questions on that?
Is there anything that we can say about the sort of global structure of the spacetime based on whether this is all of S or some proper?
Well, I mean, exploring what the boundary of the future is will lead us to Penrose's theorem, which is about black holes. But I see. You asked about the structure of the spacetime. If you care about the structure of the spacetime topologically, we completely answered it in the first week when we showed that a globally hyperbolic spacetime is the initial value surface times r. The interesting question is not the topological structure, but the causal structure. And yes, we will be learning about the causal structure of the spacetime using as tools the things I've told you about the boundary of the future. Any other questions? Yes?
Is Q in the future of Q?
Well, I define Q to be in its own causal future. And also in the boundary. The reason I do is that otherwise you'd have too many exceptional statements. So I didn't have to, okay. You see, if you looked at my proof, the proof I sketched, that the boundary of the future is a manifold. Oh, sorry. Okay. That statement would actually still be true if we decided Q is not contained in the future. Some statements I've made you need to make exceptional. You don't have to state so many exceptions if you consider Q to be in its own future. So we allow a causal path that consists of only one point. That's the way I said it in a previous lecture. So since we allow a causal path consisting of only one point, we consider a point to be in its own causal future. And similarly for any set W. So any W is in its causal future. It doesn't come to my mind right now, but when a moment comes up at which we would have to make a longer statement, if we didn't say that, I'll point it out. Hopefully that will happen, but we'll see. Yes?
I think it's like J plus being closed and boundary J plus being closed.
Well, we proved that the boundary of J plus is closed.
I'm saying if you don't include Q in the future.
Oh, that's right. Sorry. Good point. Sorry. Right. Life is much more convenient if you can say that J plus and also the boundary of J plus are closed, which I've been saying. But if we don't include Q itself in its future, we would not be able to say that the boundary, that the future. If you want to claim that J plus of Q is closed, you have to include Q. If you don't include Q, you end up saying that the union of Q with J plus of Q is closed, which would be awkward. So thank you. So So, for example, we use the closedness in making an assertion about what was the prime part of a possible prime part of a geodesic, of a null geodesic. Any other questions? Yes?
So if the space-time is globally hyperbolic,
Yes.
then there's a Cauchy surface, can we guarantee there's also another Cauchy surface, like in the future or in the past?
Well, you see, it's not hard to prove that if you have a Cauchy surface, then a surface just slightly to its future or past is also Cauchy. What's much harder to prove, and I'm not going to try to prove it in this course, is that you can sweep out the whole space-time by a family of Cauchy hypersurfaces. That's true, but it's not an easy theorem. Any other questions? You might try to prove for yourself what I just said here. It'll be easier if you assume S is compact, although it doesn't depend on that really. Try to prove that if S is compact, then a surface with any choice of time, what you mean by time, a surface within time epsilon of S, space-like surface, is also Cauchy. Okay. Now we want to navigate toward Penrose's theorem, and there are mainly two things that we need to know to get to Penrose's theorem. The first is we need to have a way to predict the existence of focal points on null geodesics. And for that we want the null version of the Raychaudhuri equation. People call it the Raychaudhuri equation, but his equation was actually the time-like version. As far as I can figure out, but I'm not 100% sure, the null version is due originally to Sachs, actually, who later went into medical physics, incidentally. So what does the null Raychaudhuri equation say? Well, so S will be a space-like hypersurface. In our application, it'll be Cauchy, but we'll say some things that don't depend on that. And then we consider W, which is a codimension 1 surface in S, and therefore codimension 2 in M. And W is space-like. So an example of W would have been this embedded sphere in Minkowski space. It's a time 0 and x equals r. That's a codimension 2 space-like surface. And as we actually already discussed, there are two families of orthogonal null geodesics that go to the future from such a surface, which I'm now calling W. They're the ones that go out, and also the ones that go in. So there are the two families of orthogonal null geodesics from W. We're going to study one of those families. So we pick one family and we make a hypersurface. It consists Y is the union of all the outgoing. We make an arbitrary choice of what we mean by outgoing and ingoing. I'll call outgoing, but what I really mean is we pick an arbitrary choice of one of the families of outgoing null geodesics from W. Now our considerations will be local near a point Q in W. So I really don't care what W is doing except near this little point. And near the point Q, these outgoing null geodesics, at least initially, describe a manifold Y. They might, if you go too far, stop being a manifold. because of the way they intersect each other and fold in. For example, well, in the actual case of a sphere, if you look at the ingoing ones, they converge at a conical singularity, and you can't really continue it past that and get a manifold. So if you go too far, you won't go to manifold Y, but we're not going to go too far. We'll see how far. We're interested in where the picture breaks down, so that's what we will explore. But we will work with the picture up until it breaks down. Now, we pick local coordinates xa, there are d minus 2 of them, for w near q. And then but we want a local coordinate system for y, and one more coordinate for y is the affine parameter on the null geodesics. In other words, a null geodesic, well, there are different ways to write the equation for null geodesics, but with the appropriate parameterization, which is called an affine parameterization, a null geodesic is described by this equation. U is called an affine parameter, and it's unique up to an affine linear transformation, U going to AU plus B, where A and B are real numbers. So I want to use U as the extra coordinate to make Y. U will tell us how far we've gone along these null geodesics away from W. But I have to say a little bit more because U isn't uniquely determined. I can partly fix U so that U equals 0 on W. A and B are in R, but A is not 0. And if our geodesics are oriented, A is positive. So the remaining freedom is that we could rescale U by a positive function. And there's no natural way to pick this function. Pick it in any way you want. All I care is that U should vary smoothly. So, the last condition I'll impose is that we define U so that, in the space-time there's a time coordinate, which we haven't got to yet, but the geodesic should have the property that dt to U is smooth at t equals 0. Smooth as a function of x. I could say it's 1, but that would, you see. I want to pick any definition of U. U is an affine parameter on a null curve that starts at a point in W. And I want this affine parameter to vary smoothly with the initial point. Beyond that, I don't care how you define it. An example of what it means to let it vary smoothly is that we would introduce a time coordinate that vanishes on S. Such coordinates exist, but there's no natural way to pick one. And then for such a choice, we would say that dt to U is, well, you could just say there's 1 once you've picked the time coordinate. That's an example of an allowed choice of U. You could make that choice of U for any time coordinate. And if you think about it a little bit, you'll see that if you replace t by another perfectly good time coordinate, t to the alpha of x, then that will rescale u by e to the alpha of x. So we're not claiming we had any natural way to normalize u, but u is well defined up to a function on this initial set w. Any questions on that? So on y we now have coordinates xa, which, well, okay, sorry. xa was initially defined only on w. But I want to extend the xa to be defined on all of y. I do that as follows. By definition, a point of y is in one of these null geodesics, and that null geodesic came from a point on w. So I just defined xa to be constant along these null geodesics. We define the xa to be constant on these outgoing null geodesics. So now we've got coordinates xa and u on y. The freedom being that you could reparameterize the xa, and you could also rescale u by a function of the xa's, a positive function. Now it's going to be convenient to add one more coordinate to get a local coordinate system on the whole manifold M. And there's again a lot of arbitrariness in doing this. So here's W, which is contained in the initial value surface S. And we pick a coordinate in the orthogonal directions. Well, pick a function, I should call it. V on S, such that W is the set V equals 0. And near W, the set W epsilon, consider the set W epsilon defined by V equals epsilon. They're supposed to sweep out S near W. So near W, you could build S out of a one-parameter family of copies of W parameterized by V. Again, there's a lot of arbitrariness how to do that. We just pick sort of outgoing vector fields, and we extend the coordinates xa we had on W to functions on S by saying that they're constant along these little orbits. And then we define V by how far you've gone on this orbit. So now, V and xa are local coordinates on S, and VU, well, in a moment, I want to extend U so that I want to extend all of this to get local coordinates on M. To do that, I now consider the outgoing null geodesics. The goal is to get a nice coordinate system on M. We look at the outgoing orthogonal null geodesics from W epsilon for each epsilon. So by the same logic as before, on W epsilon we get coordinates. Well, I'm not sure how to draw the picture, but on each outgoing null geodesic from one of the W epsilons, we say that xa and U and V are constant. So what we arrive at is a coordinate system, VU and xa, where the curves V equals xa equals constant are all null geodesics. To get this, we first had the coordinates v and xa defined along S, the initial value surface. Then we look at the orthogonal null geodesics, and we just define the functions v and xa so that they're constant along the orthogonal null geodesics. So now we have the whole manifold swept out by some null geodesics, each of which is orthogonal to one of the w epsilons, and such that each of them is described by v and xa being constant. So what does the metric look like in this coordinate system? Well, we must have GUU equals 0, just to make v equals xa equals constant null. But to make it a geodesic, it means we satisfy the geodesic equation. The only coordinate that depends on u is u itself, and its second derivative with respect to u is 0. So this vanishes. And the only dx alpha du that's not 0 is for x alpha equals u, in which case we get 1. So this is just gamma mu uu. And gamma mu uu is a half g mu nu times du g nu u minus 2, I think, minus d nu g u u. But g u u is 0. So we learn that, I'm afraid that I don't like my index nu because it looks too much like a v. So I'm changing it to beta. And likewise, mu is not a good choice. Mu looks too much like u. To make the equations more legible, what we learn is that du of g beta u is 0. That's from the condition that these curves are all null geodesics. Now, it's also true that GUA is 0 at u equals 0. That's the condition that the geodesics are orthogonal. So, since the u derivative of GUA is 0, we learned that GUA is identically 0. GUV is not 0, but it's independent of u. And in fact, it can't be 0, or the metric would be degenerate. So what we get after all this, and it was a little messier to explain it on the blackboard than I was hoping, I'm just going to write down the most general metric that has the property we just deduced. So that's the most general metric that's consistent with what we learned on this blackboard. But before doing anything with it, there's one more simplification we might make. By a transformation u going to u plus f of u, v, and x, where we pick f to equal 0 at v equals 0, we can set GVV to 0. You see, du dv will transform into dv squared times the v derivative of f. So we don't care what f was at v equals 0, but with the suitable choice of what's the derivative of f with respect to v, we can get rid of GVV, whatever it was. So then we put the metric in the form we'll actually use, slightly simpler than this, or slightly more useful. Well, in a moment we'll have to do a calculation, and the calculation is easier if you put the coordinate system, the metric in the coordinate system I'm going to state. So we get the official version of this coordinate system. Where Q is independent of u at v equals 0. Since we redefined u, we changed q, but we redefined u in a way that was trivial at v equals 0. So q is still independent of u at v equals 0. So this is sort of a canonical form for the coordinate system, to put the coordinates in this situation where we were studying orthogonal null geodesics. You might remember that when we were studying orthogonal, when we were interested in time-like geodesics, we considered a family of time-like geodesics from a codimension 1 surface. And then we very quickly found a canonical form for the metric. This is the analog of that for null geodesics. Why was the derivation longer and messier, actually? It was longer because we were interested in geodesics not from a codimension 1 surface, but from a codimension 2 surface. And as the applications unfold, it will become clear that that was the right thing to do. But it inevitably led to a longer derivation because since we were in codimension 2, I had to explain what is u and what's v, whereas in the previous case, I only had to explain what's the time. Moreover, in the previous case, the time was just the proper time measured on a time-like geodesic. But here there was no analog because u and v are trying to be null coordinates, especially u is a null coordinate. And therefore, I had to explain that we were picking it as an affine coordinate and all that. So this is the analog of what we got much more simply when we were discussing time-like geodesics.
Didn't GVV be c squared?
What did you say?
Do you mean GVV to be roughly c squared?
Oh, sorry. GVV is not 0. I should not have claimed GVV as 0. GVV, as you say, is c squared. But importantly, u is a null coordinate. We're not going to be very interested in what v does. In fact, I'm sure there's a more abstract explanation of this where you avoid talking about v. But because of the fact that u was a null coordinate, we had to define it as an affine coordinate that we normalize in an arbitrary but smooth fashion. Now, the null Ricciardori equation is just the Einstein equation RUU equals 8 pi g TUU at v equals 0. That means on y. Sorry, yeah, on y. Now, well, that's the null Ricciardori equation for y. Y, remember, corresponds to epsilon equals 0 in this picture. We could have taken any other value of epsilon and constructed a null Ricciardori equation for that epsilon. But since we singled out the surface v equals 0 in this step, our coordinate system is better adapted to the surface v equals 0 than to other surfaces. Now, I'll say the same thing I said when we were discussing the time-like Ricciardori equation. If you've ever computed the Riemann tensor, you know that's usually painful. But this is a case where miraculously it's not painful. One finds that RUU is, well, minus a half du of the trace of G inverse duG minus 1/4 of the trace of G inverse duG squared. So to write that out in more detail, the inverse, so G is the metric tensor GAB, and the inverse metric tensor is the same thing with the indices up. So this is what I mean by the trace of G inverse duG. And likewise, I could write the trace of G inverse duG squared as GAC duGBC times GBD duGDA. So that's a calculation that anyone who wants to learn general relativity should do once, in my opinion. So I'll probably put it on a homework exercise for Thursday, but I won't do it in front of you on the blackboard. Now this has the same structure that we had before when we were doing the time-like case, except that the part of G which we're using is now only the spatial part. So the G that appears in these formulas is a D minus 2 by D minus 2 matrix. In the time-like case, we have D minus 1 times D minus 1. So I think it's quite miraculous that you get exactly the same structure, except for a metric tensor with one less index. Now it's convenient to define A, which is called an area element, which is the square root of the determinant of GAB. The terminology area element is adapted to 4 dimensions, where the codimension 2 surface W is of dimension 2, and therefore a volume element on W is what's usually called an area element. So this is traditionally called an area element, although that's really 4-dimensional language. Then we define theta to be A dot over A, which is a half the trace of G inverse duG. And it's also traditional to let sigma be 1/2 of the traceless part of G inverse duG. So I remove the trace. All I've done was to take the matrix G inverse duG and subtracted its trace. With a 1/2, that's sigma. And then the Einstein, then RUU is minus theta dot minus theta squared over D minus 2 minus the trace of sigma squared. That's miraculously the same we had in the time-like case, except that there D minus 2 was D minus 1. So therefore, everything we said in the time-like case will have an analog. And we'll discuss that in detail Thursday and then prove Penrose's theorem. But I'll just close by writing down the Ricciardori equation. So the equation RUU equals 8 pi g TUU comes to be du theta plus theta squared over d minus 2 is minus trace sigma squared minus 8 pi g TUU. So obviously we'll get similar results to what we had previously if TUU is non-negative. For TUU to be non-negative at each point and each local frame is called the null energy condition. And the null energy condition is a far more robust condition than the strong energy condition that we used for Hawking's theorem. Remember, the strong energy condition is violated, for example, by the Higgs potential in the Standard Model. The null energy condition is satisfied in every reasonable relativistic field theory, all standard ones. So the right-hand side, unlike Hawking's theorem, which required some assumptions about matter, here the right-hand side is universally negative. And therefore we will be able to draw conclusions that are far more robust. But we'll do that on Thursday, I guess. So I'll just stop now and ask if there are any more questions.
I guess I didn't understand. So in our particular choice of W, right, we placed Q to be in the boundary, right, the point. Could we have done the same construction for some point inside? Like, do we even need W to be? It's closed because it's a free adjoining point, right?
No, sorry. W was any codimension 2 set.
So it could be
The conditions were local along W, so W didn't have to be closed. W was a codimension 2 submanifold.
But if V is a continuous function, then W is a pre-image of a point, right? So it should be closed.
Well, it's closed in a neighborhood parameterized by V and the other coordinates.
Okay, okay.
It was a local picture. Your argument's a bit fallacious. There's a W, it might be, let W be an open disk. Then when we added V, we made an open disk times an open interval. The open disk is closed in that set, but it's not closed in the whole spacetime. No, but to be less technical, the point is that the considerations were entirely local along W.
Exactly. Okay, that's true.
So we'll stop here. I'll just say that we need to do two things. One is to understand that the coordinate system we constructed only breaks down due to focal points. We'll explain that Thursday, but it's quite analogous to the time-like case. And then we will use this equation to predict focal points. And that will also be quite analogous to what happened in the time-like case. And then we'll introduce Penrose's notion of a trapped surface and prove Penrose's theorem. But I'll see you Thursday. If any of you did the homework, please feel free to hand it in.
So where do we hand it in?
You can give it, if you have a paper copy, you can give it to me or to Aaron. Our friendly TA is in the third row. If you don't have a paper copy, you could send it electronically. Again, to me or to Aaron.
Sorry.